In this video, we're going to look at some examples of Coulomb's law. And in another video, you learned that Coulomb's law is the force that describes the attraction or repulsion of two charges. So if we have two charges, let's say Q1 and Q2, and they are separated by some distance, let's say distance d, then the force that these two charges will feel is equal to K times the charge of each object, so Q1 times Q2, divided by the distance that they are separated squared. And so this will tell you the magnitude of that force, and if they are like charges, then they will repel, so the force would be in that direction for each charge. And if they're opposite, then they would attract. And this is really interesting because this is very similar to the force due to gravity on two objects. The force due to gravity looks exactly like this, but instead of charge, it would be mass. So charged objects, the way they attract or repel, behave in a very similar way to how objects fall to the earth, okay, just on a very small scale. So let's go ahead and look at some examples here. In this problem, we have two charged objects that have a repulsive force of 0.08 newtons. If the charge of both of the objects is doubled, then what is the new force on that object? So what we do to solve these problems is we're going to start out with Coulomb's law. Now, we have this constant K out front. Okay, this is a proportionality constant. The number is equal to 9 times 10 to the 9. The units are kind of weird. They're Newton meter squared per Coulomb squared. But we're not going to have to know this. Okay, we're not going to really use this value, and we don't need it here because we're just trying to figure out by how much this force will increase, and that constant never changes, so that doesn't affect anything here. Okay, so we're going to ignore the constant, and I'm just going to write out the quantities in that formula other than that constant. So we have Q1, Q2 over distance squared. Okay, and what you can do to solve these is we're going to put a blank spot in front of these for the factor that we're multiplying those by. Okay, and we're multiplying distance possibly by something. Okay, and then what you do is we're going to read through that problem, and here it says that the charge on both objects is doubled. So that means that we're going to double Q1 and double Q2, and we're not changing the distance at all, so you can just get rid of that blank spot or put a 1 because a 1 doesn't change anything. Okay, and if we do that, then what we're going to get is 4. I'm just multiplying the 2 times 2 here. We're going to get 4 times all of that stuff again, so Q1, Q2 over distance squared. And this is just that force, so this is 4 times that force. And so the amount that charge is going to, or sorry, the amount of force for that new force is 4 times the old force. So this new force is going to be 4 times 0.08 newtons. And so we're going to end up with a force of 0.32 newtons. So that's our answer here. So we quadrupled the amount of force. If we look at this next example, it says that the distance separating the objects is quadrupled, but the charge isn't changed. So to figure out what this new force is going to be, and I'll write this is new force, we're going to set it up just like before. So we have Q1 times Q2, and we're going to leave blanks in front of those because we don't know how they're going to be affected. And then something's going to happen to distance, and we square all of that. Okay, so we don't change the charge on either object, so we'll just leave that alone. But then it says that we are going to quadruple the distance. Okay, now if we do that, then what we're going to end up with is a 1 in the numerator And in the denominator, we're going to end up with a 4 squared, which is 16. And so we end up with a 1 over 16 q1 q2 over distance squared. So if we quadruple the distance, that means that we are multiplying that force by 1 over 16 to get the new force. So increasing the distance between the charges is going to decrease the amount of force being applied. Okay, hopefully that makes sense, right? If you think about if we were to take the moon and separate it from the Earth a further distance, the Earth wouldn't be pulling on the moon with as much force. And I'm just using that analogy because force due to gravity is very similar to charge. All right, so now we can just take 1 over 16, multiply it by 0.08 to get the new force. And so the new force is going to be 0.005 newtons. All right, let's look at this example here. Let's set up everything the same way. So we have this new force is going to be equal to Q1, Q2 over distance squared. And we're going to put blank spots in front of each value, and it says that the charge on one of the objects is tripled. So let's say Q1 is tripled, and then the distance separating the objects is also tripled. Okay, and then nothing happens to this other charge, so we'll just put a 1 out in front. And so now to figure out by what factor that force is going to change, we multiply the numerator. So we have 3 times 1 is just 3. And then in the denominator, we have 3 squared, which is 9. So we have 3 over 9 times that old force. And so that's going to be equal to 1/3 of 0.08. So if we triple one of the charges, but also triple the distance, then let's see what our new force is. So we get 0.027 newtons.